Welcome back to the Deep Dive. Today we're diving headfirst into, well, frankly, one of the biggest challenges facing AI right now. It's this incredible, almost dizzying growth of large language models, LLMs. They're getting smarter, like exponentially.
Yeah, the pace is wild.
But that intelligence, it comes at a pretty steep cost. We're talking massive computational demands, huge memory burdens, things that, can really strain budgets and push our machines to the absolute limit.
Definitely. It's a real scaling problem.
Exactly. So the big question what everyone's asking is,
Yeah.
how do we keep making them smarter, more capable, without basically hitting a resource wall or breaking the bench?
Yeah. How do we keep this train going?
Well, there's this really exciting solution making serious waves that tackles this head-on. Mixture of experts, MoE models.
MoE, yes.
So in this deep dive, we're going to unpack exactly what MoE is, why it's turning out to be such a game changer, and how a major tech player, Kakao, developed its own cutting-edge MoE model. It's called Kanana 1.5 15.7b A3b. Bit of a mouthful.
It is, but the tech is fascinating. Our mission today, really, is to explore that core MoE concept. We'll delve into the innovative ways Kakao actually trained their model, look at the performance gains they got, which are significant, and then sort of zoom out. What are the broader implications for where AI is heading?
Okay.
So by the end, you listening should have some really practical insights into how these complex AI systems are being built now. Built to be, both way more efficient and more powerful. It's like a shortcut to getting up to speed on this.
Excellent. Okay, so let's unpack that core problem first. When you interact with a traditional LLM, what we call a dense model.
Right, the standard approach.
Yeah, it's pretty straightforward in a way. You ask it something, give it a prompt, and every single one of its parameters jumps into action for that computation.
Think of it like, the whole brain lighting up for every single thought.
Exactly. So the bigger the model, like Kakao's own Kanana 1.5 8b, that's a dense one, the more knowledge it can store, which is great for performance, obviously.
More parameters, more knowledge capacity.
But, and here's the kicker, the larger it gets, the more expensive and just plain difficult it becomes to run. Because that computational load, it just scales right up with the number of parameters. It's a fundamental limit, really. Hinders scaling.
And that's where MoE comes in as this, quite elegant solution. It sidesteps that exact limitation.
How so?
Well, instead of using all parameters for every input, MoE models intelligently select and activate only a specific subset. A small group of specialized experts for each task.
Okay, like specialists.
Exactly. Imagine, going back to the brain analogy, having dedicated sections that only fire up when you're doing, say, math or writing music or remembering something specific.
Right, not the whole thing every time.
Precisely. This selective activation is absolutely key to solving that scaling problem you mentioned. It allows for much more efficient operation without really sacrificing the overall knowledge the model holds.
That makes a lot of sense. And I guess that efficiency is why MoE is gaining so much traction now.
Absolutely. It's huge, and mainly for two big reasons. First, building hyperscale models.
Right, the really enormous ones.
Yeah, dense models they hit a wall. You can't realistically build them to the extreme scales we think we'll need for future AI, but MoE changes the game. It lets you build models with hundreds of billions, even trillions of parameters.
Trillions, wow.
Yeah, like DeepSeek V3, it has something like 671 billion total parameters, but only activates maybe 37 billion for any given task.
So you get the massive knowledge, but not the massive compute cost every single time.
Exactly. Or Llama 4 Maverick, 400 billion total, but only 17 billion active. You get that huge capacity without the crippling cost per interaction.
Okay, that's one big reason. What's the second?
The second is achieving inference cost efficiency. This is more about practical day-to-day use.
Okay.
MoE can maintain really high performance, but drastically cut the computational costs of actually generating a response. Because, like we said, only a small part of the model is active.
Like Alibaba's Qwen 3 model, the 30B one.
That's a perfect example, yeah. Qwen 330B A3B. It gives you performance like a 10 billion parameter dense model, but uses significantly fewer active parameters when it's running.
Got it. So it's cheaper to run for the same level of smarts.
Pretty much. And the second point, that inference cost efficiency, that was Kakao's main focus with their Kanana 1.5 15.7b A3b model. Their specific goal was, let's get performance comparable to our existing 8 billion parameter dense model, the Kanana 1.5 8b.
Right.
But do it using 2 to 3 times fewer active parameters during operations.
So same brain power, fraction of the energy costs.
You got it. which is a massive leap for actually deploying these things in the real world.
Okay, so given those benefits, how did Kakao actually build this Kanana-MoE? Let's get into the architecture.
Sure. So the core difference structurally is in the layers. Dense models use standard MLP layers, multi-layer perceptrons.
Okay.
MoE models swap those out for specialized MoE layers, and within these MoE layers, you have this critical component called a router.
A router. Like for internet traffic.
Sort of. It's essentially a traffic controller, yeah. It looks at the input and directs it to the most appropriate expert or experts for that specific task.
Okay, so it routes the problem to the right specialist.
Exactly. And when we talk about the structure, there are generally two main types based on how these experts are set up.
Okay.
First, you've got coarse-grained MoE. Think earlier models, like Mixtral. These have fewer experts, but each expert is much larger, maybe fewer than 10 total.
Right.
And they usually only activate about 2 experts per input. Each expert is basically big enough to be a full MLP layer from a dense model on its own.
Okay, fewer, bigger experts. What's the other type?
The other is fine-grained MoE. This is more the recent trend. Models like Quinn, DeepSeek. These use many, many more experts, but each one is much smaller, like 64 or even more ultra-small experts.
Oh, 64 experts.
Yeah, and they tend to activate a slightly larger number per input, maybe 8 to 16.
Right.
But these individual experts, they're too small to really function as a standalone MLP layer.
Interesting. So connecting this back to Kakao,
Yeah.
which approach did they take for
They went with the fine-grained structure, specifically 64 of those ultra-small experts, and they activate 8 of them for each input.
Okay, 64 total, 8 active. That allows for a lot of combinations, I guess.
Immense flexibility and potential for specialized knowledge, yeah.
That distinction is really helpful. So they chose this fine-grained structure. How did they actually start training it? Did they just, start from scratch like you normally would?
Well, here's where it gets really interesting. They used a pretty ingenious strategy. Instead of training from scratch, which is super time-consuming and very expensive.
Right, takes ages.
They used something called upcycling dense LLMs.
Upcycling, like recycling.
Kind of. They basically took an existing dense LLM. They already had their Kanana-MoE 1.53b model and converted it into a MoE model.
Whoa, okay, so they repurposed an older model.
Exactly. This saved them a huge amount of time and compute cost, gave them a massive head start.
Okay, but how do you do that? How do you turn a dense model into a fine-grained MoE?
Well, what they did was take the larger MLP layers from that Kanana-3B model, and they literally sliced them into 8 smaller pieces each.
Sliced them?
Yeah, just mathematically divided them up. And doing that instantly created their 64 distinct, fine-grained experts.
That's clever.
It is. And crucially, it wasn't just like copying the same small piece 64 times. By slicing the larger already trained layers, they inherently got some variety in how each new expert started out.
So they didn't have to worry about random initialization as much.
Precisely. It ensured the necessary diversity in their initial knowledge without needing a complex and often quite unstable random setup. It's like taking a general textbook and neatly splitting it into 64 specialized pamphlets, each starting from a slightly different angle.
Okay, that's a really smart way to bootstrap the process. So they upcycled the model. Then what? They moved into pre-training.
Right. They used a 2-stage pre-training process, which they optimized specifically for MoE models. It's different from standard dense model training because of that MoE structure.
Makes sense. Can you walk us through those 2 stages?
Sure. Stage 1, they used about 700 billion tokens of high-quality general domain data.
Okay, broad knowledge first.
Yep. And what's efficient here is that these upcycled models, they can often reach good performance with less data compared to starting completely from scratch. They even used a smaller experimental MoE model first to quickly figure out the best mix of data for this stage smart iteration.
Okay, that's stage 1. That's stage 2.
Stage 2, they shifted focus. Used about 300 billion tokens, but this time concentrating on high-quality specific domains, things like coding and mathematics.
Specialized training.
Exactly.
Yeah.
And they leveraged datasets they already knew worked well from their previous Kana-LLM 1.5 development.
Okay, so you're training these 64 experts, routing inputs. How do you make sure it all stays balanced? Like, how do you stop the model from just using the same, say, 5 experts all the time and ignoring the rest?
That's a critical challenge with MoE, yeah. And the solution lies in using auxiliary loss functions.
Auxiliary loss. So extra goals during training.
Kind of. They added 2 specific ones to the main training objective. The first is load balancing loss.
Okay, sounds relevant.
It is. It directly tackles that imbalance problem. It basically encourages the router to choose experts more uniformly, preventing the model from over-relying on just a few favorite experts, ensures everyone gets utilized during training.
Makes sense. Spread the workload. What's the second one?
The second is router Z-loss. This one's more technical, but it's designed to prevent numerical instability within the router mechanism itself. Just keeps the writing process smooth and mathematically sound.
Got it. So these extra losses help keep things stable.
Hmm.
Does training MoE require different settings otherwise, like learning rates?
Yeah, it does raise that important question about sensitivity. And Kakao found they did need different settings. They had to use lower learning rates than you typically would for a dense model to prevent instability.
Okay, lower learning rate. Anything else?
And quite strategically, they actually increased the global batch size later in the training process.
Increase the batch size. Why?
To further stabilize things. They drew inspiration from methods used by DeepSeek for this.
Yeah.
It just shows that, even though MoE offers efficiency, training them requires this surprisingly nuanced approach. It's not just about data. You need precise tweaks to the core training parameters.
It's amazing how those fine adjustments make such a difference. And you mentioned another clever detail earlier. They adjusted the coefficient for that load balancing loss in stage 2, the domain-specific stage.
Ah, yes. That was a really neat finding.
What did changing that coefficient achieve?
Well, they actually halved it in stage 2. And this did two things. One, it further helped stabilize the training when focusing on those specific domains.
Okay.
But two, and this is really cool, it actually allowed domain-specific experts to naturally form.
So the experts started specializing on their own.
Exactly. By slightly relaxing that pressure to use all experts equally on domain data, certain experts started to become the go-to specialists for coding or for math problems.
Oh.
It's like the model organically created its own internal specialists for different subjects. That's a fundamentally different way to think about how AI architecture can develop intelligence.
That is fascinating.
Mhm.
Okay, so after all this innovative pre-training, the upcycling, the stage training, the loss adjustments, what were the results? Did Kana 1.5 15.7b A3b achieve its goal?
The core achievement, yeah, it's pretty remarkable. Their base MoE model, the Kana 1.515.7b A3b base, remember, it only has 3 billion active parameters during inference.
Right, 3b active out of almost 16b total.
Exactly. It achieved comparable performance to their much larger dense model, the Kana 1.58b base.
Comparable with less than half the active parameter.
Yep, and in some areas, it was even better. They saw higher scores in things like KMLU, which tests Korean knowledge, and MBTP, a Python code generation benchmark.
So a huge win for efficiency right there. And how did it stack up against the model it was actually upcycled from, the smaller 3B dense model?
Ah, that comparison is maybe even more impressive. So remember, both the upcycled MoE model and its dense base model, Kanana-Nano 1.53b, operate with roughly the same number of active parameters, around 3 billion.
Right, same active compute cost, essentially.
But the MoE model showed overall better performance, and particularly in code generation, the improvement was dramatic, like a 10-plus point jump on benchmarks like Human Evil and MBPP.
Wow. So same active size, but much better performance. How?
It clearly shows how that MoE structure, distributing knowledge across many specialized experts, dramatically increases the total knowledge capacity of the model, even if only a few experts are active at any one time.
It's like having a much bigger library, but you only need to pull out the few relevant books for each question.
That's a great analogy, exactly.
And beyond just the benchmark scores, Kakao also found evidence that these experts really were specializing, right?
Yes, they did. They used techniques like heat maps and something called the Gini index analysis.
Oh.
And these analyses confirmed, visually and quantitatively, that inputs from different domains like general knowledge versus Python code actually activated different sets of experts.
So you could literally see certain experts light up for coding tasks.
Yeah. Coding tasks, for instance, heavily relied on a few specific domain experts, while general knowledge questions used a broader, more evenly distributed group. It's empirical proof of that specialization happening inside the model.
So stepping back for a second, what's the bigger picture implication of that? Expert specialization actually happening.
Well, it means MoE models aren't just about efficiency. They can naturally develop these specialized knowledge areas within their own architecture.
Which makes them more precise.
Exactly. More precise, more effective when dealing with specific types of information or tasks. It's a step beyond just scaling up raw knowledge. It's about the intelligent organization of that knowledge. And it hints at a future where AI isn't just generally smart, but may be incredibly good at specific, complex, niche problems.
And I think you mentioned there was also a positive side effect on understanding long texts. Long context understanding.
Yes, exactly. They found the MoE structure seemed to naturally help with comprehending longer texts.
How so?
They saw improvements just by making some simple adjustments to how they sampled data during training. They didn't even need to add specific long context training data initially.
Interesting.
It suggests that the way MoE distributes and accesses knowledge might inherently make it better at processing more extensive information, which is obviously crucial for things like summarizing long reports or having really extended conversations.
Okay, so the pre-training results were fantastic. Comparable or better performance with much higher efficiency. Evidence of specialization. What came next?
The post-training phase,
Okay.
right? Teaching it to follow instructions.
Exactly, that crucial step where you teach the base model to be helpful and follow human instructions effectively. And Kakao realized that, just like pre-training, post-training for MoE needed a fresh look. They redesigned their pipeline.
Okay, what were the key changes they made there? They highlighted three main ones. First, they implemented staged RL reinforcement learning.
Staged RL. Why staged?
Well, they recognized a common challenge. Different kinds of tasks often need different amounts of RL training to hit peak performance. Like, precise math problems might benefit from one duration, while general, open-ended conversation needs another.
Right. One size doesn't fit all.
Exactly. So they broke it down. First stage, SFT, supervised fine-tuning, just learning from good examples.
Okay.
Then, RLVRRL with verifiable rewards. Think tasks like math, where there's a clear right or wrong answer, so the feedback is objective.
Got it.
And finally, RLGRMRL with generative reward models. This is for the more subjective stuff, like general conversation, where another AI model acts as a judge of quality.
So they optimized each learning type separately. Makes sense.
Yeah, ensures everything reaches its peak. The second big innovation was tackling an MoE operation bottleneck.
A bottleneck.
Yeah, specifically with something called grouped GEM.
GEM. That's the core math operation, right?
Yeah.
General matrix multiply.
Exactly, the fundamental calculation that makes neural nets work. The problem was that in many existing frameworks, like Hugging Face transformers at the time, the calculations for each MoE expert were often processed sequentially, one after the other.
So the GPU wasn't being fully utilized. Lots of waiting.
Precisely, wasted resources. So Kakao developed and integrated their own custom grouped GEM kernel.
A kernel being like a super optimized piece of code for this specific task.
You got it. This kernel allowed the GPU to process the calculations for multiple experts in parallel, simultaneously, like a well-coordinated team instead of a queue.
Okay, and what was the impact of that optimization? You mentioned it was significant.
Huge. It led to a 10 times faster training throughput for the MoE layers.
10 times faster? Why?
Yeah, think about what that means for development. Experiments that might have taken days could now be done in hours. It just dramatically speeds up iteration, testing new ideas, fine-tuning, a massive accelerator for R&D.
That's incredible. Okay, so staged RL, group GEMM.
Yeah.
What was the third key change in post-training?
The third was integrating a technique called on-policy distillation, especially to boost the smaller models. They took inspiration from the Qwen 3 model here.
On-policy distillation. How does that work?
Okay, so imagine you have your smaller MoE model, the student, and a much larger, more powerful model, the teacher. In this case, Kakao used their Kanana flag 1.532.5b instruct as the teacher.
Right.
The student model generates a response. Then it looks at how the teacher would have responded to the same prompt, specifically looking at the probabilities the teacher assigned to different next words. The student then adjusts itself to make its own output distribution more similar to the teacher's.
So it's learning by mimicking the bigger model's thought process.
In a way, yes. And it's on policy or online because the student learns directly from the responses it generates in real time, comparing them to the teacher. Makes it very efficient.
And did this distillation help the Kanana-MoE model?
Yes, significantly. Especially in math and coding tasks, they saw clearer gains. And even for general conversation, while the direct gains were maybe less pronounced there, it gave the model a much better starting point for the subsequent RL training stages.
All right, so putting it all together, the staged RL, the group GMM speed up, the on-policy distillation, what was the final outcome for the instruction following model?
The final outcome was really impressive. The Kanana 1.5 15.7b A3b instruct model, again, just 3 billion active parameters, now performs comparably to a dense 8 billion parameter model.
So matching the bigger dense model.
Yes, but even better, after applying that on-policy distillation, its performance actually became higher than the 8B dense model in many evaluations.
Wow. So smaller active size, better performance.
Exactly. And this really brings us back to that question about real-world applications. What does it mean when you can deploy AI that's this efficient and this powerful?
Yeah.
It means advanced AI capabilities become much more accessible and more affordable to run. It could really democratize the use of powerful AI across many different fields and applications.
What an incredible journey we've covered today. We started with that big challenge, the cost and scale of traditional LLMs.
The resource constraints.
Then we dove deep into Kakao's really innovative work on mixture of experts with their Kana model. We unpacked how MoE works, the upcycling, the specialized training,
All those clever techniques they used.
and the results speak for themselves. Powerful AI, but with drastically reduced operational costs, better specialized skills, hitting performance comparable, or even better than much larger dense models.
Yeah, and stepping back for just a moment, this deep dive into Kanana-MoE, it really feels like just the beginning, doesn't it?
How so?
Well, Kakao is already talking about training MoE models from scratch next time, which they think could unlock even faster performance gains. And they're looking at scaling these MoE architectures to truly super large models.
So this isn't just a one-off experiment.
Not at all. It really highlights a critical path forward for AI development, a path that makes these incredibly capable models not just theoretically possible, but actually practical and accessible for widespread use. It's about smarter scaling.
Absolutely. Which leaves us with a final thought for you listening. Imagine the new applications, the new possibilities that open up when AI models can be both incredibly knowledgeable, truly vast in their capacity, and incredibly efficient to operate. How might that shift how we interact with AI every day? Could it push AI into completely new realms of specialized intelligence? Or maybe make powerful AI truly accessible to everyone?
It definitely feels like the future of AI is looking not just smarter, but also much, much leaner.
A fascinating prospect indeed.